taking 20 meters.
With basic AMA-GLA software. Okay, so this software was designed by some engineers. It's using the same engine as the basic Easy NEC software uses. So I don't know how much you guys know about antenna modeling software. There's three major ones out here right now. There's MMANA-GAL, which is kind of everyman's antenna software. Then there's Easy NEC, which is more of a professional style software. And then there's 4NEC. Yeah, I think that's right. It's 4NEC, and that one is another one of the professional softwares. Now, there's pro versions of all of these. MMANA is free. Easy NEC became free at the beginning of the year, this year, so you can download that one. The reason I wanted to start with MMANA is because you can literally draw in this software like a sheet of paper, versus the other ones where you have to understand and be able to visualize a coordinate system, okay? I don't know how many of you guys have tried to work in 3D before, okay, and try to think in coordinates, okay? So you have an x-axis, a y-axis, and a z-axis, and you got to be, you know, this point X, Y, and Z, and this point X, Y, and Z, and this point X, Y, and Z, and that's how you draw your lines, and it's all done by coordinate system. So it's a little bit different when you're trying to do that versus being able to go in and draw something, okay? Now I've gotten to the point, and you will, if you play around with the software enough, you will get to the point where you start to think in coordinates, okay? So you'll just use the coordinate input and just start typing in digits, and away you'll go. But to get started, to be able to visualize things, it's always better to draw them yourself, okay? Unless you've got a piece of graph paper and you can draw in 3D on a piece of graph paper, then, you know, God bless you. So on the screen, I'm going to move to now, you see this is MMANA in the geometry view. This is where you would enter in coordinates, okay? This is the view. This shows your antenna, and this is also the platform to which you will draw, okay, your things. Then you have a calculate field, okay? This is an input field where you put in your frequency, you set up your ground, you set up your height, you set up what type of wire you're running or pipe or whatever you're going to use for your medium for the antenna. And then you have far field plots, which far field plots kind of show you what the performance of the antenna is going to look like, okay, in a graphical format. And if you've, you know, all of you guys are licensed hams in the room, you've all seen the charts with the, you know, the two views, the plan view and the elevation view, or the azimuth view and elevation view of an antenna's performance, okay? And they have some neat tricks. We can show you 3D. We can show you currents, vertical and horizontal polarization and currents. So we'll get to that. But tonight we're just going to start with the basic stuff. So once you've got your software open, go to the View tab and hit the View tab. Okay. And then you will see at the top there's a series of buttons at the top. There's one that kind of looks like an eraser. It's a white box. When you hover over it, it says Wire Edit. Okay, click on that. And that's going to bring up another view sheet here, okay? Now you've got a scale. The scale is all in meters, all right? There's no feet in this software. It's all in meters. On the bottom right-hand side, you see where it says 3D, XY, XZ, and YZ. Those are your fields for drawing, okay? So you're going to get your coordinate system, because this is, you don't draw in 3D, you're going to draw in 2D, and it's going to produce a 3D image, okay? So your XY coordinate would be if you're drawing a flat line like a dipole, or elements that are horizontal, okay? You understand what I'm saying? If you're using the X and Z, then you're going to be drawing vertical components, okay? So vertical antennas for arrays, raised verticals, anything like that, you're going to draw on that. And then the YZ allows you to draw in that same vertical parameter, but along the Y-axis versus the X-axis, okay? So you understand what I'm saying? You've got an X-axis, which is horizontal, a Y-axis, which is horizontal, going perpendicular to it, and then you got a Z-axis, which is perpendicular to those two going vertically, okay? And subvertically. So you can actually draw, you know, in all three dimensions, positive and negative, okay? So what we're going to start off with is a simple vertical, okay? And we're going to do it for, let's just say, 40 meters, okay? Because that's an easy one for me. I work a lot with 40-meter antennas. So I'm going to go to the XZ, okay? And I'm going to go ahead and next to the little eraser above your projection, you're going to have one that looks like a pencil on a paper. It's the second box in. If you click that, that's going to allow you to draw, okay? It's right above projection where I said 3D XY, you got the little one in the center that looks like a pencil. Yeah, okay. So I'm just going to start a dot here at Z0 and X0, and I'm going to pull a line up, okay? And I can look on the side on that top right-hand corner. You can see where my X is at, you know, 0.357. And my Z is going up and I'm getting close to 10 meters. So I'm going to get this thing to about 10.5 meters, okay? And it's going to snap there. So it shows me in that box, wire number 1, X0, Y0, Z1 is 0. That's the top, that's the start of the line. So it's 0, 0, 0, dead center of that graph, okay? And then my X2 is 0. My Y2 is 0 because I didn't change anything on the X and Y coordinates. My Z0 is now at 10 meters, okay? So that means that line is 10 meters long. Does that make sense? Can I get a nod or a yes or a no? Huh? It'll just automatically snap if you get close. Now, if you need to edit it, if you need to make it a little bit longer than 10, you can always zoom down below the projection and you can zoom it, and then you can go ahead and go back to that eraser thing next to it and then grab the point and pull that point, you know, another half meter or a meter, whatever you need. Now, see, I made it a meter, so that box is a meter at this point. So if I stretch a little bit further, I can grab it and bring it down. And now it's 10.5. See how I'm doing that? Using the wire edit. Are you following, Brian? Okay. Yeah, you can. So if I were to go out of here and I left it at 10, right? And I wanted to change that value, I can hit OK at the bottom of the screen. It's going to take me to my view and it's going to show that line, okay? And then I can always go to the geometry tab and I can change that figure, that 10.5. I can make it 10 and hit the tab key, and now I've got it at 10. And if I go back to the view, it's going to shorten that line by half a meter, okay? So if you draw it close, then you can go in and edit it via the coordinate system, or you can zoom in and change it. Does that make sense to you? Okay. Anybody have any questions about drawing in the system? Right. So if I wanted to draw, let's say I wanted to draw another vertical, okay, and I wanted to be 5 meters away from this vertical, okay. Now I can look and see if I go on my x-axis, I can take my little cursor and I can move over until the x equals 5. You see where it's happening? Down here at the x here, if I move it here, you'll see it'll say x equals 4.9, 4 whatever, okay? So now I know I'm 5 meters away. I can hit my pencil button, come back to that spot, and I can go ahead and draw in another one and make it 10.5. Okay, or 10 meters long, however I want that thing to be. Does that make sense to you? Now, if I want to get rid of that, I can use the third button, which will allow me to select it, and I just hit delete, and it goes away. Okay? Now I'm going to go back and edit this because I want this line to be 10.5 because I know that's pretty close to what I want for 40 meters. So I'm going to edit this and make it 10.5. Okay, it's 10.5. All right. So now we're going to hit OK. So now we got our wire sitting on the ground, going up 10.5 meters. Okay, does that make sense? Now, we don't have any coax attached to this, right? So we have to give this thing a source. Now, there's a couple ways you can do a source. The visual way of doing it is in this View tab. You can click on the wire, and then you can right-click it, and it's going to give you Add or Move Source, okay? And there's 3 places you can put a source on the wire: beginning, end, and center. Okay. Now with a dipole, we always try to feed those things in the center, right? For monoband dipole, you're going to feed it in the center. For vertical, we want to feed at the ground, right? For this particular antenna, since it's a ground-mounted vertical. So we're going to set the source at the beginning of the wire. Okay. And it brings that little red dot up. Make sense? Okay. So if I select the wire, right-click the wire, and I hit Move or Add Source To, okay, it gives me the choice of center of the wire, beginning of the wire, or end of the wire. Okay. Now, since this is a ground-mounted vertical, and I started my wire at the ground and went up, I want to put that source at the beginning of the wire, okay? Because I'm going to feed it right at the ground. Does that make sense? So I select beginning of the wire, and I get the little red dot here at the base. Does that make sense? Okay. So now I have a piece of coax hooked to this thing. Okay. So now I'm ready to start playing with this antenna to see where it's at. So if I go to calculate, okay. Okay, so go to the view, go to your wire, right click on your wire. Okay, it brings us up that box, right? And see where it says Add Move Source To. Now if you highlight that, it'll give you 3 choices. It'll give you center of the wire, beginning of the wire, end of the wire. Beginning of the wire. Okay, you click that and it'll put a little red dot at the beginning of the wire. Okay, so now we're going to go to the calculate box. Okay, we said we're going to make this antenna for 40 meters. Okay, so 40 meters, 7 megahertz band, right? So we're going to go ahead and I'm just going to put this thing in dead center of the band, which is 7.15. You can enter that value at 7.150, or you can select it. It's here in the drop-down box. Those are common frequencies. So I set that there. Now, if I want to look at this thing in free space, which be, you know, basically no ground, I could put this thing here, but it's going to be all kinds of weirdness because there's no ground plane for this thing to reflect against, right? I can go against perfect ground, which here in the Carolinas, anything that we have here is not going to be perfect ground. Perfect ground is going to be something like, you know, right around, you know, salt water, those kind of things where it has high conductivity. You're going to have high Siemens count per meter, those kind of things. We're going to use real ground, and we're going to set this thing up for real ground. Yes, Wade. Oh, you were driving. Okay. So single ground. So we're going to go to ground setup. Okay. Now for this area, ground setup, next to real. You see it? Okay, so when you click that box, you get a dielectric, you get a conductivity, you get an R value, which is the radius of the wire, okay? And you get a height. Don't worry about height because we're not doing raised radials. We're doing ground mount just only right now. Dielectric around this area, and for most places, unless you have something like you're in the mountains where you got a granite, granite base, those kind of things where you're very little dirt, your dielectric is going to be 12, 13, 14. So just leave it at 13, okay? For this area around here, our ground conductivity depends a lot on where you're at in the Carolinas as regards to whether you're in the Sandhills, whether you're here in the Piedmont, whether you're towards the mountains. And it even varies a lot around this area because of clay deposits in marshy areas and those kind of things. If you leave it at 4 or 5 millisiemens per meter, you are going to be fine. It's going to be pretty darn close, okay? The way you figure that out is you actually put a megger in the ground and you take and you look at the conductivity on the megger, right? We're not going to go through all that deal, right? We know the ground conductivity around this area is somewhere between 3 and 5. And in real terms, 3 and 5 are not much difference, okay? So if you wanted to kind of hit it right in the middle of the road, you can put 4 in there. I always leave it at 5 for this area. Now, if I'm down at the coast, Myrtle Beach, the island, Hilton Head or on Folly or those kind of areas, I'm going to increase that because your conductivity is 1,000 times more down at the beach. So instead of 5 millisiemens per meter, you're at 5 Siemens per meter. Okay, it's a big difference. Okay, and you'll see. I'll show you that. But for our purposes, we're going to use 5 millisiemens for right now. So 5.0. Okay. Now you have ground radials, so you can turn on radial boundary. Okay. Now the thing about this program is it expects the radials that are ground mounted radials or even aerial radials to be at a quarter wave. Okay. So it's going to figure on that. So if you tell it I have four radials in the number, it's going to give you 4 quarter wave radials. Okay. There's no changing that radial that I know of right off the top of my head. There may be something in setup you may be able to change it in, but for our purpose tonight, just think you're going to be at quarter wave radials. Okay. So let's change that number to 4, and we're going to use 4 radials, and we're going to use a wire radius of 0.8 millimeters. Okay. That's equivalent to about between 12 and 14 gauge wire. Okay. And you can pull an AWG to millimeter chart up and you can figure out, and you can change that wire. Okay. That wire size. So if you use something smaller, you can change it. But for radials, it really doesn't make that much difference. Okay. Now, height above ground. Okay. That's the next box down. We've got a ground mounted radial, so a ground mounted vertical. So we're not going to do anything with height above ground. Okay. With this one, because we want that thing sitting on the ground. Make sense? Okay. Material. This is where you choose what you're going to use for your antenna. You've got copper wire, you've got copper pipe. So if you wanted to do, like a J-pole antenna out of copper tubing, you've got aluminum wire, you got aluminum pipe, you've got steel wire or iron wire. FE is iron, but it's steel wire. So like if you use horse fence wire, that changes the property of the antenna a little bit. You use a wire so you can actually go in and define your own wire. Okay. Just for our purposes tonight, we're going to start off with copper wire. Okay. So now we've got, and if you go to the geometry tab real quick, we've got a ground mounted vertical that's sitting dead center of our coordinate grid on the ground, 0, 0, 0. The top of it is at 0, 0, 0, so it's straight vertical, plumb, at 10.5 meters long, and we're using 0.8 millimeter wire, which is going to be 12 to 14 gauge wire. Okay, so you can see that right across your number 1 wire. Okay, All make sense? Okay. Go back to your calculate tab. Now, since we've got this all set, we're just going to hit that start button at the bottom. Okay. Now it's giving us the frequency of 7.150. We have 40.3 ohms of real resistance. Okay. We have 23.75 ohms of imaginary resistance. Okay. And if you remember, when you talk about impedance for antennas, it's a complex number. So you have an imaginary and you have a real number. Okay. The real number is measured in ohms. The imaginary number is measured in ohms. And what that imaginary number piece is stored energy. Okay. Because we're dealing with electromagnetic waves. So we have a magnetic component involved in this. And so that magnetic field is stored energy. Okay. So if you look at the SWR, we got 1.76. Now that is based on a 50 ohm load. So we're using 50 ohm coax, no bowing, 50 ohm coax straight back to our radios. And we all know our radios want to see a 50 ohm load, right? So we're doing our SWR comparison of our antenna impedance to our expected impedance of 50 ohms resistive, and it gives us 1.76. Okay, does that all make sense to you guys? All right. So, yes. Yep. It's reactance, yes. So you have capacitive reactance and inductive reactance. It's a positive number, so we know it's capacitive because you're on the ground, so you have magnetic field stored on that ground plane. So you've got a capacitive reactance. If that number was negative, it'd be negative 23. We'd be talking about inductive capacitance. Okay, so it's an inductive reactance. So it's a little bit different, but if you go back and watch that first primer I did on antennas that I did the presentation on and I put up on YouTube, it'll go deeper into those imaginary and real numbers. Okay, the real number we want close to 50. We want that reactance as close to 0 as we can get it. Okay, but for purposes for us, if we wanted to operate this antenna on 7.15, guess what? It'll be fine because it's below 2 at that point in time. Okay, our radios are going to be fine with it. It's not even 2 SWR, so your radio's going to be fine. How efficient it's going to be is a little different. Now your front to back dB, that's going to be directivity of the antenna. So if it favors anything in any direction, it would show up there. Okay, elevation angle, that's where your maximum gain is. So this is showing you a 26.5 degree angle of elevation is your maximum takeoff angle. So that's where your maximum point of radiation is, and I'll show you that here in a second. Ground is real, and we're almost all of our polarization is vertical. Okay, where it says vert here. If we were dealing with dipole, it would say HOR for horizontal. Okay, so now let's go to the far field plots tab, which is the next one over. Okay. And now you're going to see what that antenna far field looks like. Okay. The one on the left is the azimuth view. Okay. So if I take my cursor and I go here, okay. So if you say your azimuth 0 degrees is north, okay, and you sweep around, you'll see that thing change, right? So now we're east. So now we're south, now we're west, okay? Does that all make sense to you? You're looking at this thing from a bird's eye view down on the antenna. That antenna is sitting here at the direct center, okay? And your degrees around the compass are here, okay? Now that black line is your maximum gain point, okay? So that's how much gain you have. And you can see the gain is up here in the center. You'll see gain 0.3 dBi. Okay. So 3 dBi is 0.3 dB better than an isotropic radiator. Okay. An isotropic radiator is a theoretical antenna It's infinitely small. It's in free space and radiates in unity gain in all directions at the same rate. Okay. So it's just a comparison. All right. So when you talk about dBi, you were talking about the gain against an isotropic radiator. Okay. A perfect radiator in free space. So you have a little bit better than a radiator in free space. Okay. Now, when we start talking about antennas comparing to, you'll have a difference. Excuse me. You'll have a difference in dB, and you're going to talk about it in dB, right? Not dBi. dBi is strictly gain against a set model, which is the isotropic radiator. Okay. So now when you look at the left side of the equation, right, we've got the elevation plan. Okay. So this is showing your elevation from ground level up to vertical. Okay. And remember we said that lobe where we were at, where maximum gain was at 26.5 degrees, right? So you can see where that thing reaches out here as farthest point. It's right at between 27 and 26 degrees. That all make sense to you? Yes? Okay. So there's also a button down here that says 3DFF. Okay. That stands for 3D far field. Okay. Go ahead and click that. Okay. And of course, it's going to put it on the wrong screen for me. There it goes. Okay, so let's bring it up here. Okay, so that's what the RF field looks like in reality. Did you get that? What did you get? A little box with an XY cursor? Just click the little box at the bottom. There's a little box that says like 3 or something. Yeah. That's something new. This just changed in the software. I haven't seen this same thing before either. Okay. Usually I get a wire model up here. So this is something new I haven't seen. I was kind of surprised. But this is our model of the RF field. Okay. And you can see color intensity at 0 dB is that bright pink. And the dark colors down towards the bottom are negative dB. So there's losses. Okay. Now, we talked about an isotropic radiator being a dot with a sphere of radiating energy around it. Okay. This thing looks like a darn donut, right? It's got 2 big lobes and it looks like this, right? Well, that's because we have the ground sitting there reflecting this stuff and we're actually squeezing that RF, right? So instead of unity gain, we're squeezing that RF. It's like squeezing a balloon, right? And the air's got to go somewhere, okay? So it's going to go out the side. So it's going to bulge out the sides. It takes out of the middle and bulges out the side. That's why you see a little bit of gain, okay? Now we can close that box right now. I just wanted you to see the 3D, what the 3D model looks like. We can go back to this model and we can actually look at slices of elevation. And we can say, okay, this is at, what does it say, 26.5. We can put this thing and say, okay, we want to see what a takeoff angle is for a long haul DX, which is somewhere between 5 and 10 degrees typically, okay? And we all know why that is because the lower that takeoff angle is, the longer that radiation travels before it's refracted and sent back to Earth, okay? So when you start talking about refracting a radio wave, okay, every time that radio wave refracts, you lose energy. It attenuates. Okay, so when we set energy up, we wanted a low. If we're going for DX, right? We want a low radiating angle, so we get a longer distance to travel before it refracts. Excuse me. And then it'll refract off the atmosphere at that same angle and it'll return down, right? And either if it's long enough, it'll refract again off the atmosphere, or if it's shorter, it'll refract off the ground and bounce back up to the atmosphere again, okay? When conditions are really good and you've got a low takeoff angle, there is a point where you can refract all the way across the globe and come back to yourself. But that's here and there. Now, that's only one portion of that wave. We saw that whole wave front here, right? On this bubble, there's radiation going out from all of those. So you've got some radiation going out, a small portion of it going out at 75 degrees, a small portion going out at 40 degrees, a big portion going out at 26 degrees, and a smaller portion going out at 5 degrees. Okay, so that big bubble of RF, you got to think of it as a planar front. Okay, so you're seeing that whole thing move. It hits the atmosphere at different times and drops in different places. That's why sometimes you'll be strong into Texas and strong into California and strong into Hawaii, and then weak into Asia or South Pacific, because different points where your radiation is going and how many times it refracts and how many times it attenuates. Okay, does that all make sense? Right, yeah. So when you output, there's attenuation, and you have your signal strength going out, and it attenuates at a certain rate. Okay, and there's a specific term for it, and I can't think of it right off the top of my head now. But as your power density, right? You lose power density as that wave expands and moves away from your source. Okay, and it attenuates when it gets the atmosphere, because it's not a perfect refraction, right? Because the atmosphere is not an eggshell where we're broadcasting inside the eggshell. It's actually more like cotton candy, right? So some of that RF is going to pass through the atmosphere, and some of it's going to get refracted back. Okay. Now, when the SFI is really high and the D layer doesn't absorb too much, and the E layers are refracting and the F layers are refracting really well, and they almost become like they're solid surfaces, then you get that kind of almost 100% refraction. But typically, when the SFI isn't really high, it's more like cotton candy. So that stuff will bleed through the atmosphere. Some of it will get knocked down. It just depends. Okay. But again, we're getting a little bit off topic, but we can take a look at this and say, okay, we want the elevation at 5 degrees. We change that calculation, and you can see that circle shrunk, right? Now we're seeing negative 6 dBi, 6.2 dBi in that circle. Now, that's just a layer of that elevation, right? It's not the whole picture. It's not that whole 3D model. It's just a layer, right? So we cut it at 5 degrees off the horizon versus 26.5 degrees off the horizon. Does that all make sense to you? Okay. Now, the other things that's cool about this stuff is you go back to the calculate, right? And at the bottom, there's a button here that says plots. Okay. You hit that plots button, and it's going to bring up this little menu. Okay. If you click SWR, right, it's going to bring up an SWR chart. And you see where it says BW here in the right-hand side? That's bandwidth. So you can decide how big you want this bandwidth to be. So let's just do 400 kilohertz, okay? So that's going to take us from 6.95 megahertz all the way up to 7.35 megahertz. Okay. Now, why did I choose that? Well, the 40-meter band is 7 through 7.3, right? So we can take a look at this antenna's performance on SWR all the way across the band. Okay. So if we hit the detailed button here, it's going to draw our SWR curve. Now, you can see it's lower on that low side of the frequency, right? I intentionally made this thing long, okay? Because I wanted you to see the curve, right? And the relationship is, if my antenna is long, it's going to be better on the low side of the band, and if my antenna is short, it's going to be better on the high side of the band. It's like a piano wire, okay? So if I hit a piano wire, if I hit the low notes, they're always longer wires. If I hit the high notes, they're always shorter wires. Does that make sense? So the relationship is longer wire, lower frequency, shorter wire, higher frequency, okay? So we want to see where this antenna is resonant. Where are you having problems, Billy? Okay. So if we want to look at resonance, we can also choose the button resonance. Okay. Now it's going to show the resonance of that antenna is somewhere around 6.951. Okay. Now, we all know resonance and SWR are not the same thing, right? A 1-to-1 SWR does not necessarily mean that antenna is resonant. Okay. It means it's going to be highly efficient, but it doesn't mean it's going to be resonant. Resonance occurs at one frequency and one frequency only, and that is when your load is purely resistive at the load required for the transceiver. So if I have a 50 ohm load, wherever that antenna, the reactance is 0, so the imaginary part is 0, that is where my antenna is resonant. That is where I'm going to put the most power out. Now, it may not be an SWR of 1-to-1. It may be an SWR of 1.2-to-1 or 1.3-to-1 or 1.5-to-1, because your real part of your equation of your antenna impedance may be 36 ohms when it's looking for 50 ohms on the, but your reactance is 0. Okay. So my load is completely resistive. So all my energy is being radiated. Okay. So I have no energy stored in that magnetic field. I have no reactance at all on the antenna. Everything's being radiated, but it doesn't necessarily mean my SWR is going to be 1.1 to 1.0 to 1. Does that all make sense to you? I see a lot of confused looks for a second there. Okay, resonance and SWR are two different animals, 100%. Okay, you have to consider SWR is a comparison of impedances. Okay, your 50 ohm purely resistive load against whatever your antenna is showing you at that frequency. Resonance is where your reactance is 0 and your load is completely resistive, okay? And when we talk about resistive loads, that is where you get maximum power out, okay? When you're purely resistive, whether it matches good or not to the antenna, all the energy being sent is radiated, okay? None of it's stored, it's all sent out, okay? So don't equate SWR, a good SWR, to resonance, okay? A good SWR is important, don't get me wrong, but doesn't mean your antenna is good. I can give you a dummy load with a great SWR, but it doesn't mean I'm going to get out very well, okay? I can give you a 50 ohm load that'll, you can put a 50 ohm light bulb there and it's going to light up, but it doesn't mean it's going to get out very well, right? When that load is purely resistive, it's going to get out, okay, at that particular frequency. Does that make sense? Okay. So, yep, Theo is. Okay, I haven't seen Vicky yet pop up. Okay, so one of the other things we can do is we can take a look at, go back to SWR and go to detail, okay? And we can see that thing's low at about 6.1 or 6.9951, somewhere in that neighborhood. So I know I have to shorten this antenna. So back to geometry, and let's take half a meter or quarter meter off of it. So I'll make that 10.25, right? I'm gonna go back and hit my calculator button. Now my SWRs come down quite a bit, right? I'm at 1.35. My resistive load is 37.34. my reactance is 3. So my reactance gone down. I'm getting closer to resonance on this antenna. Y'all follow me? So if I go to my plots now, and I pull up SWR, I change it back to 400 and hit my detailed, I'm almost dead on, right? And if I hit my resonance is dead on. That's the lowest, that's the resonance I'm gonna have. It's resonant at 7.15. Now, there is a in here, and I've got to find it because this thing changed a little bit. I didn't think they made any changes to this thing, but there is an X versus R plot where you can actually see the X is the reactance. You can see where the curve is, where it goes to 0, and you can see where your R curve goes to 50 ohms. Okay. Now, that's the basics on getting started with this thing. Okay. Now, I'm going to draw a quick dipole because I don't want to take up too much time in this meeting. But we're going to go ahead and you can file a save this if you want. So you just hit the little tab at the top where it says save as, the little blue disk, and allow you to save it. Just name it vertical or whatever you want to. And it'll give you a start. Okay. Now, one other thing I'm going to show you, if you go to open when you downloaded this thing, it's not what I wanted to do. I don't want to save this one. I don't care. Cancel. File. Open. There are some antennas built into this thing. Okay. So if you go to the antenna file, so if I back that up, if I go to open, it has a folder labeled antenna. If I click on that, you can see there's HF beams, HF multibands, HF simple, right? If you click on simple, you're going to see verticals, loops, dipoles, right? So there's some stuff in here built that you can pull up and change and play around with, okay? But if you wanted to take a look at a dipole, I'm just going to go ahead and do a new antenna real quick. So if I go to my view, I've got nothing on the view. I go to my wire edit. I'm going to do X and Y, and I'm going to draw a dipole for 20 meters. Okay. We all know half wave dipole, right? If I'm on a 20 meter band, I need a 10 meter wire, right? That makes sense to y'all? So I'm going to go in here and I'm going to draw a 10 meter wire. So there's a 10 meter wire. That's a 20 meter wire. I don't want that. That's 40 meters. Let me delete that. Let me just draw this here. Okay, there I got a 10 meter wire, okay, for X and Y. I'm going to go back to the view portion, and this thing's laying on the ground, right? So I'm going to add a source to the center of the wire. So now I've got about 5 meters on either side, okay? And I'm going to go to the geometry tab. I'm going to look, and my X2 is 10, my X0 is 1. So this is basically a 10 meter wire laying on the ground. If I go to my calculate, I'm going to calculate at 14.150, which is close to the middle of the band on 20 meters. Now I'm going to raise this thing off the ground using additional height, and I'm going to put it at 10 meters. Okay, so that's half a wavelength above the ground. I'm going to go to my ground setup. I'm going to turn off my radials because I don't want any radials under this thing. And I'm going to go ahead and hit the button to calculate. Now, it's giving me an SWR of 277. So I know I'm probably long on this thing, more than likely. So if I go to SWR, I'm going to go to I'm going to set it for 400.
my detailed. Actually, I'm short. That's right, because 20-meter band is actually about 21 meters. So I'm going to go back to geometry and I'm going to change this. I'm going to make it 11 meters. And go back to calculate. Start. Ooh, made it worse. What the hell did I do there? Plots, did I make it too long? I bet you I did. Detailed. Yeah. Yeah, I made it too long. So geometry, 10.25. Should be close. No, 10.25. Come on, change that. And go to calculate. There we go. That's a little better. Okay. So now I can look at my plot and I could say my SWR. That's a little short. Okay. But for our purposes here, let's not care about the SWR because we want to look at the far field plot. Okay. And our far field plot, of course, it's an antenna, it's a dipole, right? It's going to look like a peanut. So you've got the antennas along the x-axis here, and my y-axis is where I see the gain, okay, off the sides. And then I've got, you know, this kind of shape here. My maximum lobe's at, where's my lobe at? 47 degrees is where my maximum takeoff angles is. But I can change that height, and let's change it to, let's put it one wavelength above the ground and calculate. And our far field plot's going to look a little bit different. Okay. So height above ground is going to play some difference in this. But now I'm seeing 5.6 dB of gain. Okay. At that angle. So, but play around with it. You got the basics now how to draw this stuff in. Use the antenna file and pull stuff in so you can see how it's built. Look at the geometry tab. Okay. So you can start thinking about the coordinate system, X, Y, and Z. Okay. You know, it's really simple once you start to think in that coordinate system of how to place stuff. And geometry is going to play a big part in this. So dusting off your high school geometry of how to figure out, you know, the base of the height of a triangle or Pythagorean theorem, those kind of things start to really play nicely in. Just remember that there's a couple of things with dipole antennas. When you do an inverted V on a dipole, okay, the antenna is going to be shorter than it would be for a flat top. Reason being is when you bring those ends of that wire close to the ground, you're going to pick up capacitance off the ground. So typically an inverted V is going to be 4 to 5% shorter than a standard dipole would be for a flat top. Okay. Just those kind of things you'll find out when you start to do this, but don't get frustrated if you get in there and you design an inverted V antenna and you're like, I can't get my SWRs right. This thing works as a flat top. Why does it work as an inverted V? Capacitance. Okay. You're going to pick up capacitance off the ground. Anybody have any questions? Did I go too fast? Okay. So we're going to do this in a series of things. We're going to get more complex. So play around with this. If you have questions, right? Email me, call me. Most of you guys have my phone number. Text me, email, and say, hey, I need 5-10 minutes, whatever, to go through this stuff. And I'll go through it with you, you know, kind of on a one-on-one basis if I can. And I'll answer questions. And the next one we'll bring it back in and we'll start to do it. We'll do step by step again on a vertical, just building it and playing with it. And then we'll go to a dipole and we'll start playing with a dipole. Okay. And then we'll start talking about more complex systems, Because once you figure out a vertical and a dipole, and you understand how this stuff works with it, all of a sudden, all these other complex antennas come together. Vertical arrays, dipole arrays, Yagis, log periodics, all that stuff will come into play. Because all a Yagi is, quite frankly, is dipoles that are, one is fed and the other two act like a reflector and a director, okay? Or a two element, you got one fed and one director. So you got one that's a little bit longer, and all it does is push RF in one direction, okay? It's a series of dipoles. A four square or a vertical Yagi always is a series of verticals. If you understand vertical antennas and you understand dipole antennas, at that point in time, once you have those down, then it's just putting the pieces together to puzzle. Because you understand what the picture is, all you got to do is figure out how the pieces work, right? What's the difference between the distance between my driven element, my reflector, my driven element, my director, the distance between my verticals. Do I want 1/8 spacing? Do I need 1/4 spacing? Do I need 5/8 wave spacing? Those are the things that you'll have to think about. You won't worry about the antenna piece of it. It'll be spacing and those kind of things. So, excuse me, I'm sorry. Once we do dipoles and verticals and you get those two down, everything else is just pieces of a puzzle, okay? You just build machines from those simple pieces. Make sense? Okay. Again, if you have questions, don't hesitate to email, call me, or text me, and I'll help you as much as I can. Mm-hmm. I could just go to this menu in here and fill out all those pieces. Mm-hmm. So you're just testing it. Mm-hmm. This is going to give you an approximation of what the antenna will form. Now, keep in mind, this is a model. So with any kind of model, whether it's a health model, an electrical model, an antenna model, a climate model, it's only as good as the information you put into it, okay? So if your ground setup's wrong, it's different than what you put in here. Yeah, you put the wrong material in, you build it out of something else, all bets are off, right? This is only approximation. I use this to kind of say, okay, this is what this antenna should perform like, and that makes a decision for me. Yes, I'm going to build it and physically test it. Versus, yeah, I'll just go out and throw this wire out and see what happens, kind of shit. You know, excuse my French, but you know, I got too little time to play around like that. I'd much rather have it here and know that, hey, you know what, this is going to probably work for me. I'm going to go out and build it and test it, right? Instead of just going out there and wasting money and wire and coax and ferrites and everything else, toroids, trying to build this stuff. And again, this antenna modeling software is not the best one in the market, but it's the easiest one to learn. Once you get the concepts on this, we can start talking about EasyNet, which I'm getting kind of proficient in now. And that one gives you a little better approximations. Well, that's, so you, with EasyNet, you've got to do everything in coordinates. You got to do everything in your head. Yeah. Yeah. I don't know who was here the night we were talking about antennas and talking about modeling, and I said I was building a cubicle quad, 2-element cubicle quad for 6 and 10 nested. And we went in the back and I wanted to show them the antenna, and I had the coordinates in my head, so I just programmed everything in and it drew it out and put it up. And they're like, how the heck did you do that? I says, I've drawn this antenna like 25 times. Those numbers are stuck right here. So, all right. So we're going to end this portion now, and I'm going to turn it over to Mr. Wade.
CQ 20 meters.